Do you remember last time we concluded that it's going to take me O of m log n when I'm using a heap? We did the math. It's O of m log n. Okay, in this case, when would be the worst case? Why the worst case is n square log n for a heap? We said it's m log n. M as in Mark. And here it's n square when the worst case. Why? Who can tell me? Melanie. Very good. So when I have a complete graph, when I have a graph like this, when all the edges are connected, this will get me the m will be n square. Okay? So that's why I'm going to. So now if we go back to the other question, when we have a complete graph, it's going to be worse because it's based on m. And if I have a complete graph, m is going to be n square. Now this will take n square log of n. The unordered sequence will take what? Always. It's not based on anything because always I have to search. Even if they are ordered, I don't know they are ordered. It's unordered sequence. I have to search. So it's going to take me n square all the time. So in this case, in a complete graph, which one is worse? This one. So in a complete graph, when I have a maximum number of edges, it's not good to use a heap. It's better to use unordered. But when I know that I will not have the maximum number of edges, m log n, which is in this case, the m log n can be n, for example. N log n is better than n squared. Okay, so that's how I want you to think about it. You can check this also and see more details. Now, I also took, if we go here in the recap. So if I go to the recap, guys, so we covered all of this in the WOOC lab. Here, I left for you this. This is from the book. You can read it also. It also explains when to use heaps, when to use unordered. And the conclusion is when we have the heap implementation with the number of edges and the graph is small. Okay? Very good. Now we want to go to the minimum spanning tree. So what do you mean by minimum spanning tree? Let's first remember, what is a spanning subgraph? What is a subgraph? Subgraph is when I'm, for example, I'm only visiting 3 nodes out of all the nodes. Okay, that's a subgraph. Spanning subgraph is what, guys, if you remember? It's when I'm when I'm visiting all the nodes, but not all the edges. Okay, that's spanning. When we add the word spanning, that means I'm visiting all the nodes, but I'm not visiting all the edges. Now, what about a spanning tree? Riley.
Span a subgraph, but there aren't any cycles.
Very good. So that means a spanning tree, I'm visiting all the nodes. This is a spanning tree. I'm visiting all the nodes, but what? But there's no cycles. That's a spanning tree. Now, the minimum spanning tree, guys, is that when I'm visiting, when I have a spanning tree, but when I add the weights of the visited ones, it's going to be the minimum weight. Okay, so that's the idea here. Going to be what? The minimum weight. That's called minimum spanning tree. These are some of the applications. Who can tell me why it's usually it's very important? Minimum spanning tree is one of the, yes, Joel.
For example, in a train station at Ottawa, we can see what's the shortest path to different stations.
Very good. So actually, what if you don't want to use the Google map to go from a destination to another destination? It's not like I know that I'm here in the side and this building, and I want to go to, I don't know, I want to check what is my shortest path from here till the side building. So I have a source. That's why the other one is called what, Dijkstra? Single source, shortest path. You know the source. On Google Maps, you always have to put the what, where are you, your place, and then the destination. Minimum spanning tree, no. What if actually, I'm planning to see what is the shortest path in this university, if I want to visit all the buildings, no matter where I am, if I'm in the site or I'm here and I want to use this map, it's always going to end up having the shortest distance. Okay. So let's give another example. We still do these things, but we used to do this when we used to play video games back then. We used to do LAN. We still do that because everything is online now. But yeah, when we used to build our own LAN, LAN, LAN network, you have to use it through what? Cables. It has to be cables, not routers. So minimum spanning tree is what you need to actually use if you want to save on cables. Because if you want to calculate all the stations, and the usual, we used to call them like, the video game places and stuff, to save on the cables, you do the minimum spanning tree. How can I connect all the stations together with what? With the minimum number of cables or the minimum length of cables. Yes.
Connected each station to each other instead of to a switch or a hub?
Yes, so that's what we're saying. So you do this, you can do the switch, you can do, but we're saying if you want to do that, you use a minimum spanning tree. Why? Because you want to do the minimum, we want to figure out what is the minimum length of the cables that you're going to use. So that's the idea here. For the other thing, there's so many different things. We're going to cover a few other applications in the WOO club. So now, let's make it a bit more understandable. What's the difference between the single source shortest path and the minimum spanning? Look at this, guys. Both of these are spanning trees. Am I correct or wrong? Both of them are spanning trees. Yes. Is there any cycles? No. This doesn't have a cycle. This doesn't have a cycle. Correct? Okay. If I'm using the single source shortest path, this one, this tree here, and I want to calculate all the weights. So let's see what would be the total. So first, the goal is to find the shortest path from the source to every other node. So that's the goal. I need to have a source. A minimum spanning tree, the goal is to find the minimum cost. So the difference is here, as we said, in this case here, I have this. So let's take a look now and the other. Okay, total weight of the graphs. Here, if you add 1 plus 4, all of this, you're going to end up with 23 as the total weight. Okay, so 1 plus 4 plus 6 plus 3 plus 2 plus 7. Now for this one here, if you add the weights, which is the differences between this and that, what's going to have 26. Okay. So if you use the minimum spanning tree, you're going to end up with actually less distance to visit all the nodes. Now, what is the difference? Does this mean that this one, I should never use it? No, because look, even though the total distance here of the MST is 23 and it's better, if I want to go from here to here, so from here to here, which one is going to be better? The MST is going to be what? 4 plus 1. I cannot go from here. Plus 6 plus 3 plus 7. 21. In this case, it's going to be what? 4 plus 1 plus 10. 15. So here it proves to you that it depends on the application. Like if what I want, my problem is that no, I want to check from a source, from a specific source. I know the source, and I want to go to check the shortest path. Usually that's when we go with the single source shortest path, which is like Dijkstra. But if no, I just want to calculate what is the minimum path to all the nodes. So in this case, if I'm here, okay, this is minimum spanning tree. So that's the main difference. Okay, guys, so this is the main difference between the two. For you, always remember, if you have the source, that means it's Dijkstra. If you don't have the source, it's a minimum spanning tree. Okay, so let's talk now about the properties. So we have two properties when it comes to the minimum spanning trees. Yes.
Shortest path and lecture same thing.
Yeah, so single source shortest path can be a BFS if you have the same weight, and can also be a Dijkstra if you don't have the same weight. And there is also other algorithms. So Dijkstra falls under the SSP. Now the same thing, MST is a minimum spanning tree. We can implement it using Prim, or we can implement using Kruskal algorithm. So these are like more the names of the concept. So there is two main properties for the MST. One of them is, if you look here, let's look at this. Is this a minimum spanning tree? No, I'll save you the work, is because here, if I choose this one, that's 7, better than 8. So the idea here is called cycle property. That means each time in any cycle, so this need to be dotted, okay? These are dotted. So whenever you look at the cycle, usually the one which is not visited need to be the highest. So look here, 2, 6, 8. Always the one not visited is the highest. So that's it's called the cycle property. The same thing here. I have 3, 8, 7. But here I have what? 3, 6, 8, 4, and then we have 7. So we can switch 7 by 8. So this is just called the cycle property. And this is going to be used for Prim. So we're going to understand this better when we give the example of the Prim. Very simple. If the weight here is less, we're going to choose this one. Now, in another words, take a minimum spanning tree in any cycle of the graph. The non-spanning tree edge dotted line has the max weight. Again, check the dotted line is always going to have the maximum weight inside any cycle. So 6, 3, 7, 10 is the highest. 3, 2, 5, 5 is the highest. So that's called the cycle property. Now the other one, which we'll be using for what? For the Kruskal, is called the partition property. What do you mean by this? Let's assume these are one component, and this is another cloud here. This is not a partition. And you have to choose one of the edges. If this edge is 7, and this edge is 7, can I switch the edges and still have this what? The same thing. So these two are two different minimum spanning tree, but will cost the same thing. So the partition is just when you want to, if you have two equal edges, you can choose between them. Okay, you can switch from here. Good. So we're not going to go too much on this. So let's start from the first algorithm. Now, for me, if you understood Dijkstra, this is going to be the easiest part because almost the same exactly as Dijkstra. But there is one small trick. Hopefully, you don't forget this in the exam. So let's see. Dijkstra, do you remember we said Dijkstra cannot be used on a non-connected graph, correct? It has to be a connected graph. So I can't use Dijkstra on this graph. The same thing for the Prim algorithm. I cannot use it on a non-connected graph. It has to be connected. Okay, so that's one of the main things. Now, let's go right away and I'll explain it to you. I'll explain it from here. So we're going to follow the same thing like we did with Dijkstra. I have here 2, 8, 4. Where should I go? 2. Now, in Dijkstra, what did we do here when I went to 2? Riley.
We updated the values on the node based on the path that we're getting past we found.
Very good. So technically, we updated all the adjacent nodes to C. We updated B, E, F, D. How did we update them? So, for example, 2 plus 7, that's 9. I'm not going to update it. It's 8 here. 2 plus 1, that's 3. Correct? Okay. The only difference between Prim and Dijkstra, when I update, I'm only going to use the edge. Okay? It's as simple as that, but you need to remember it. Okay? In Dijkstra, we added 2 plus 7. That's 9. 2 plus 1, 3. Here, no. Here, we're just checking that's 1. So is 1 better than 4? Yes, I updated. Is 9 better than infinity? Yes, I updated. Is 3 better than infinity? Yes. Now, is 7 better than 8? Yes. So in this case, I'm going to update. In Dijkstra, I didn't update the B because I had to add 2 plus 7. As simple as that. In this case here, if I do this, which one is my next step? I have 1, 9, 3, 7. Where should I go? 1? Okay. We go to 1. What should I do in this case? Who still didn't get the idea? I go to D because it's 1. So what is the next step? We add D to the cloud and then we have to update. So how am I going to update? Which node I need to update? Veronica. The node adjacent to D. Which one? I have F. F is 9. Should I update it or not? Yes. Okay. How should I update? What should I replace 9 with? 5? Exactly. In Dijkstra, we used to do what? 1 plus 5, that's 6. Here, we're only updating with the edges. Is this clear, guys? Clear? Okay. So let's do it together then. So I'm here. I'll update this to 5. Then now, which one I should choose? I have 3, 5, 7. I'm going to choose. Yes, Melanie.
Sorry, at first, F is infinity.
Yes,
You would replace it with 9.
with 9.
Then you can replace it with 5.
Because now I visited D, right? I chose 1. So I expanded like this, right? I have to update all the adjacent nodes to the new node that I added. So I added D to the cloud. Now I need to also update everything connected to D.
First, when we updated it to 5, it was 9.
Yeah. So is 5 better than 9? Let's go back like this. Let's clear this.
So, okay, no, that's good. Yeah.
Good? Okay. So we go here now. I'm at 1. This is 5. Where should I go now? The common mistake in the exam is that you think because you're at D, you can only go from D. That's not the case. Is this a queue? It's a priority queue. And the priority queue, you can go from any minimum, right? Any place. Let's say you're using priority queue. It doesn't have to be the last one you visited. So that means I'm going to the minimum one, which is the minimum is the 3, correct? I'll go to the 3 now. If I go to the 3, which one I need to update? B is the only one connected to E. B is 7. The edge is 2. Should I update it? Yes. So it's going to be, I go to 3. I'll update B to 2. And then I'll go to B. Correct? At the end, the last one is going to be F. Okay, so let's do it together, guys, on the WOOC lab. This one, I didn't spend too much time explaining it, guys, because it's the same exactly as Dijkstra. So I'm assuming it's still fresh. So hopefully, guys, if you understood this now, on Monday, we have the tutorial. The tutorial will cover Dijkstra, Prim, and Kruskal. That means, what do we have so far? We already have a recording and a tutorial for DFS, BFS. We're going to have on Monday for Dijkstra, Prim, and Kruskal. So it shouldn't be too hard for you to remember for the final. Yes, that's it.
A review session, the final.
Most probably it will be one of the tutorials or the last session here. It depends. If I finish the sorting early, we're going to do a review session that will try to solve previous midterms, previous exams. So
What more lectures do we have? Like,
3 left. So we have next Tuesday, Thursday, and Tuesday.
and then
So the last day is December 4. December 3 will, what is the last day? Okay, the fourth is the first day.
the last day.
3rd is the last day. Is it the 3rd or the 4th, the last day? The 3rd? Okay, what I can do. We can try to do it on Monday, the 2nd, instead in the tutorial, and maybe Tuesday you don't have to come, so you can prepare for if you have exams. So we'll try to do something like this. Maybe we'll do it on Monday, and then Tuesday we'll cancel this. So we'll take the lecture to the tutorial, and then you don't have to come on Tuesday. I'll think about it and send you an email. Okay, so let's start. Is this a spanning tree? Is this a spanning tree, guys? Let's try to everyone to participate. 50-50 so far. Okay, we'll start with yes. Why is this a spanning tree? Riley?
Does the 9 mean that it's not connected?
No, there is a red line here because I manually fixed it. So this is not a spanning tree because there is a cycle. Okay, there's a cycle here, so it's not a spanning tree. So this is no. Is this a minimum spanning tree? See my Photoshop skills. Is this a minimum spanning tree? What do you mean by minimum spanning tree? It's a tree. We're visiting all the nodes. We don't have any cycle, but it has the minimum weight, the minimum total weight. So if you do the calculation, it's also going to be no. So if you add 5 plus 2 plus 7 plus 6 plus 1 plus 4, it's going to be greater than if you included the 3 instead of the 5. If I'm trying to find what is the minimum total number of kilometers in the city I need to walk to visit all my friends' house, which algorithm is better? Like you have a very caring friend. Which algorithm in this case? SSSP or the MST? Guys, here we're back to the bigger picture of critical thinking. You're computer scientists and engineers. So we try to find the problem. So here there is a problem. And we want to solve it. You remember we said problem, algorithm, and then the other things. So problem, this is my problem. Which algorithm I should use? You want to answer? Let's wait for everyone. So 2377. Joel, you want to answer?
Oh, I picked MST because I assumed because we're not starting at a specific point in the city. You just said in a city in general. So from any point, would MST be able to find what's the shortest path from one house to another house?
Ralph, you had your hand raised.
Yeah, I was saying MST because we have an actual destination. So from one point to another, let's say from one node, so that'll give us the shortest path.
Okay. Who wants to say Dijkstra?
Yes, that's shortest path.
I made you doubt yourself. Are you sure? Okay, if you want to visit the houses of all of your friends, you have to start from somewhere. So how? Maybe that's why some of you chose Dijkstra. Right.
We don't know, sorry, the one line is better also have, because the best one. That is better if you know what you're doing.
Very good, guys. So you shouldn't doubt yourself. If you, Ralph, Joel, you answered very well. I'm giving you something else. Veronica helped. No, MST, I don't know from where to start. Now, from a practical perspective, how can we solve this? Let's assume you want to know, because you want to go walking there, and you want to know which one is the shortest in general. let's say now if I'm dropping you by my car, if I drop you at any of the houses and then from there you want to visit all the houses walking, it's going to be the shortest path. Okay, so if you started from any of the houses, it's going to end up with the shortest path. Okay, very good. Now, if I'm trying to find what is the shortest route in the city to take, if I want to go from my home to visit my professor's house, which algorithm is better? Why this is happening? Dijkstra, Prim, or BFS? So if I'm trying to find what is the shortest route in the city to take, if I want to go from my home to visit my professor's house, which algorithm is better? Who wants to tell me which algorithm that we don't want to even consider first? So let's minimize. We have 3 options. We want to bring them to 2. Okay, sorry. New faces have the priority. It's a priority queue based on new faces. Yes.
Well, we wouldn't want to use BFS because we might have different lengths of nodes.
Very good. Thanks. Very good. So we took out BFS, we took out Prim. I ended up with Dijkstra. I have to use Dijkstra. So usually, if you know right away, you know that I'm going from my home. So the first one that I should take out is actually Prim's. Now I take out Prim because I have a source. BFS and Dijkstra will both work, but here it's a real life application. All the streets are the same distance? Of course, no. So that means we have to use Dijkstra because the different ways, that means different distances. Yes.
I will clear us to you know where you're starting from. If we were trying to visit all the houses and we knew where we're starting from, we'd still use Prims and not Dijkstra though, right?
No.
That's right.
You remember in Dijkstra, guys, the question here, repeat the question in a loud voice.
So if we're still trying to visit every single house in your friend's neighborhood or whatever, and you knew where you were starting from, don't we still want to use Prim because we're visiting every single one and not Dijkstra?
Do we need to use Prim because we want to visit all the houses, even if I know that from where I'm going to start? If you go back to the slides of Dijkstra and BFS, we said if you give BFS or Dijkstra only one node, that means you're telling Dijkstra or BFS from this source, go visit all the nodes. But if you give 2 nodes, that means go from this to that. But originally, if you go to the slides, if you remember, even in the algorithms, we pointed out that if you add another node, that will be from point to point. But no, BFS and Dijkstra, if you give them one source, it's going to visit all the nodes automatically. Okay, so again here, guys, it's going to be, of course, Dijkstra. Let's do the Prim together. I'm here at A. Where should I go? Let's do them faster because we have to cover Kruskal. Kruskal is very, very easy, to be honest. So quickly, I have 2, 8, 7. It's going to be B. Very good. B because B is 2. Now, you're at B. Okay, let's assume you went from A to B. Which nodes needs to be updated? It's a multi-select. Which nodes need to be updated, guys?
Where you're going next.
Have C and D. Okay, very good. That's correct. Why C and D? Because these are the nodes adjacent to B. These are the nodes connected to B. Now, what would be C? Raise your hand. 5. Guys, remember, Prim, only the edge. Dijkstra, 5 plus 2. Okay? So it's going to be 5. D is going to be what? 7. Very good. Now we went here. I'm at B. Which one I need to visit next? So what do I need to look at? Infinity, I don't touch it. I have 7, 5, 7. So which one I need to go to, the longest route or the shortest route? Do I have options here? There's no options. I'm looking for the shortest route. I'm going to go with the minimum weight. So it's going to be for sure C. Correct? Now you're at C. Which nodes are going to be updated? Ralph.
Just a question, if E had the shortest amount of weight, imagine I had like 4, can we go from B to E? From A because we're
Yes. This is a cloud, as we said. From any place of the cloud, you can go. So what we are asking here, let's assume E had 3. So we have 5, 7, and 3. Can I go to E? Yes. Right, guys? From any place of the cloud, this is the cloud, I can go. It doesn't have to be from B. So now, which one is the next one? None. So we had D. Why do I want to update D? Who said D? D is 7, and I'm at C. So I have 9. 9 is greater than 7. Of course not. I'm not going to update it. 9 is greater than 7. Correct? What about E? E is 7. 8 is greater than E. I'm not going to update it. So it's none. Now, this is Kruskal. We're not going to do it now. So let's go back to Kruskal, and then we will continue this. So this is the same exact one that we saw in the WOOC lab. It's in the slides. So we're going to do it all. Now let's look at this one. How does Prim works? It takes the first property of the MST, which is what the cycle property. That means each time there's a cycle, we're going to go with the minimum weight. So that's the idea behind it. Now, this one, I'm not going to go through it. Why? Because the same exact one of what? Of the Dijkstra, the same exact thing. What's different in this code from this code? Which line is different from Dijkstra? Yes.
It's a node with the number with the edge, not with the.
Exactly. So that's the only line that if you compare both algorithm, that's the only line. The other one, it's the same exact thing. It's a priority queue. What are we inserting in this priority queue? We're inserting the vertices. So we are inserting the nodes, but based on what? On the key, which is the weight of the node, right? So we have a priority queue, and then the only difference is that here we're using just the weight of the edge. There we're adding it. So again, so if we do it, we're not going to spend time on it. If we do it, it's going to end up with the same exact thing. It's going to be M log N. What is the worst case of this? You should be bored now. N squared log N. When it's going to happen? When it is full graph. Now Kruskal. Kruskal, the reason why it's good to use it sometimes, because what if you have non-connected graph? If you have a non-connected graph, then you can use Kruskal. Why? Because the difference between Kruskal and Prim is that Prim, we used to have one node, and we add things to this node, and we expand. Kruskal, no. Every single node is its own cloud. So we start like this. Every single node, its own cloud. And you can expand from anywhere. And Prim and Dijkstra, if you're, let's say you're here, and you want to go, you can't reach F because it's still infinity, for example, right? Unless something is adjacent to F to be able to update it. Here, no. Here, every single one is its own cloud. So how do we add it? We look at the edges. So it's still, I'm going to use a priority queue. Okay? the difference between this priority queue and the priority queue of the other ones, the priority queue has the nodes inside it. Here, we have the priority queue of the edges. So we're going to store all the edges inside the priority queue. And then if I'm looking at the minimum number, it's going to be the minimum weight of the edges. So what is the minimum weight of the edges? Which one is?
Maybe.
AB. So that will be the first one. What would be the next one? So let's say we have we had a priority queue like this, and we had all the edges. We have, for example, AB. We have BE, and then we took this out because that's the priority. We're going to continue to find which one is the minimum. It's the minimum priority. So which one is the next one? Ralph? Yes, exactly. So instead of looking at the weights which is going to be accumulated at the node, like previously we need to update the weight of the node. Why? Because it used to include the weight also of the edge or something. Here we only look at the weight of the edge right away. So the second one is 2. The third one. And if you notice, I don't have to go from A or B because they are one cloud. I can just jump to H and F. D. 3, exactly. The next one. Joel.
G and F.
Very good. So let's continue the WOO clap. It's very simple if you get it. Kruskal is super simple. So what is the next one here? Looking for the minimum edge. The edge with the minimum weight. So we have BC, CBC, BC, BC, BC. Everything is BC. Let's take a look. BC, where is BC? BC, that's 5 here. So that's 5. Very good. So let's take, that's correct. Let's go with the next one. What is the next one? I have AC, AC, GH, GH, BE. Okay. So we have what? GH, we have BE, we had AC. Okay. Abed.
Does it matter what order we go, like BC or CB?
No, it doesn't matter. The edge, if it's undirected, it's the same. Yes.
All the nodes.
Here we're focusing on the edges because we want to find the route to visit, like from anywhere. So what do you guys think? We had so many options. We had GH, we had AC, and then we have BE. So let's start with GH. Who thinks GH is the correct one? Raise your hand. Who thinks it's not the correct one? They left you alone. Do you see? They tricked you, and you're the only one who thinks now it's not GH. Let's prove them wrong.
When that make a sample, then
Very good, guys. Kruskal is the simplest, easiest way to solve in the exam. It's so quick. And then because it's super quick, you made a cycle. And this is not a tree anymore. So GH, if you do it, it's a tree. Sorry, it's not a tree. It's not a minimum spanning tree. So you can't use this. So we're going to use AC.
No.
Exactly. So we're going to use BE. Because AC is also it. There is a cycle. So that's why the next one is actually BE. So what are we learning? We're learning that these all three algorithm Dijkstra. So the hardest one was Dijkstra to understand, but then Prim is the same as Dijkstra if you remember that you only need to copy the edge. Here it's super simple if you remember that you shouldn't have a cycle. Okay. So the next one is going to be BE. So let's go this and go back here. So if you look, going to have AB first, HF, ED, and then BC, and then we're going to have BE, and then that's it. We're done. We visit them all. And if you notice, this is non-connected graph. Okay, in this case. Now, if I want to implement this, this works with what? The idea of having each one as its separate cloud is what? Is the second property of the MST, which is the partition. Do you remember we said you can actually, if you're looking at two different partitions, you can find the minimum between them. Now, what's happening here, if you notice, guys, we start with each one has its own cloud, let's name it. But then we're combining this. So we're doing like a fusion. So we're not going to cover the implementation of the data structure for this one because usually we don't cover it in the scores. But if you go on the book, even in the book, they are going to mention which data structure you're going to use, but they are going to say they're not going to expand on it. It's something called union, okay, that we're not going to cover it here. Now in Java, they use the comparable class that you can implement it with the comparable class. But the idea, if we want to take a look, is this. Main thing that's different is that there is a priority queue, but we're storing the edges, not the vertices inside the priority queue. That's what you need to know. Then if you look at it here, we said it's using the partition property. And then that's how you're going to think about it. That's what you need to know in this course. That's what we're going to cover. This looks like similar to what if you want to implement this? Yeah, but like more like data structure wise. So this is kind of like what when you have something like this and then inside it you can do it. So it's like which is the Abed
Table.
positional list. It's like a sequence, for example. You have a sequence, but these are sequence of linked lists. So these are like a linked list thing, but each one has also inside it. So it's like you can implement it with a positional list, but ideally, Kruskal is implemented with something called union find. That's the data structure, but it's not covered in our book. Okay. Usually, Kruskal, if you want to give it, we give it to you as an assignment usually to do it yourself. Try to do it, for example, without libraries and stuff. But this is what you need to know here is that, again, this will also be O of M log N. So everything we've learned is M log N if we're doing a JCC list. Dijkstra, Prim, and Kruskal, M log N. Okay? Okay. And now let's do this together. And we're going to end up with this. Find the minimum spanning tree for the following graph using Kruskal algorithm. CE. Next, Riley. DE.
G. Next after D.
We didn't go DC because 4 here will what? Do a cycle. So we're going to go with DG. Next. We see anyone? Yes. BC. So let's check. Do I have 5, 6? Can I take it? No, there's a cycle. So the next one is going to be 7. So I can say BC. Next one. Yes. AC. So AC, yes. James, you wanted to.
Yes, AB and AD might work, both of those cycles, so it's actually, no, AD does work, no, that's work.
Very good. So it doesn't work because you don't only have to look at the 3, you don't have to look at the 4 nodes. So AB is not going to work, AD is not going to work. So which one?
Yeah.
Yeah. DF.